Hello! In this video, we are going to prove the following theorem. Let C be a real number. Then for all positive integers n, we have that for all lists of real numbers a1 through an, this sum is equal to this sum. Okay, now let's start out the proof. Let's give ourselves a real number C. And our goal is to prove that for all positive integers n, that this is true. And since we're trying to prove a statement about all positive integers, let's use induction. So let's start with the base case. In the base case, we're trying to prove that this is true in the case where n is equal to 1. So really, we're trying to prove for all lists of real numbers a1, we have that this is equal to this in the case where n is equal to 1. So give me an arbitrary list of real numbers a1. So now, let's prove that this is true in the case where n is equal to 1. And to see that, well, let me rewrite the left-hand side where n is equal to 1. Now, since the lower and upper bound are the same, we know that this sum is just going to be equal to cai, where I is equal to 1. However, we know that a1 is just the sum from I equals 1 to 1 of ai. So as you can see, we have shown that this is equal to this. So we've shown that this is true in the case where n is equal to 1. So this completes the base case. Now let's move on to the induction step. In the induction step, we give ourselves an arbitrary positive integer n where this is true. So let n be a positive integer and assume for all lists of real numbers a1 through an, this is true. The whole goal of the induction step now is to prove that this is also true for n plus 1. So we're trying to prove that for all lists of real numbers a1 through an plus 1, that this is true, where instead of n, we have n plus 1. So give me an arbitrary list of real numbers a1 through an plus 1. Our goal is to prove that this is true, where instead of n, we have n plus 1. So really, to do that, let me rewrite the left-hand side where we have n plus 1 here. Now really, since the n plus 1th term is strictly greater than 1, we can take the n plus 1th term of the sum and pull it away from the rest of the sum. So really, we can rewrite this as the sum from I equals 1 to n of cai plus can plus 1. But then, we would like to use our induction hypothesis to say that this sum is really equal to this. Can we do that? Well, yeah, we can. Right? We know that our induction hypothesis works for every list of real numbers a1 through an. Well, we have a list of real numbers a1 through an right here. So this must be true. Which means we can replace this sum with this. And now notice we can factor out a c. But now notice what we have inside this parentheses. We see that an plus 1 is really the n plus 1th term of this sum. So really, we can rewrite this entire thing as the sum from I equals 1 to n plus 1 of ai. So as you can see, we have shown that this is equal to this. Which means we've shown that this is true, where instead of n, we have n plus 1. And that was the whole goal of the induction step. So this completes the induction step. And because we've completed the base case of the induction step, this closes the induction. Which means we have proven for all positive integers that this is true. And that's exactly what we wanted to prove. So this completes the proof. And so yeah, that's pretty much it for this video.